Hi folks, I'm Pranshu. Welcome to my talk on the power of Cilium with eBPF, and let's jump right in. So first, let's talk about what is eBPF. In layman terms, eBPF is basically a tool that you can use to attach functions to system calls. So basically, like we have the send and receive system calls that are used to send and receive data from the machine. So if you attach functions to that, then in that case, if any application calls those functions or those system calls, your function will automatically get executed, and you can do all sorts of things there. Like you can access the data that is being sent these system calls, or you can access the data structures in these system calls, or you can perform any specific function that you wanted to when these system calls are hit. And eBPF is actually an extension or an upgrade on top of BPF. That was a tool that worked in a very similar way, but the only difference was that it was only attachable to user space functions, and it could only be used to filter packets and not perform the advanced functions that we can using eBPF. And the biggest benefit of using eBPF is its performance. So basically, you can attach all the probes that you want with minimum performance overhead, because these eBPF probes are really lightweight and they attach very efficiently to these system calls, and they definitely don't hinder your the performance of your application. So if high performance is one of the priorities for your application, you- eBPF is definitely an option that you can look for. And in terms of what is Cilium, Cilium is basically used to write the user space code for getting all the data, and everything that we have done in eBPF happens in the kernel space. So to get that data in the user space, you need to write user space code. And so for that, we use Cilium. And Cilium is not the only option out there. We have a lot of options in C++, Python, and also in Rust. The reason that we went with Cilium was that, first of all, our rest of the application was written in Go, and Go is definitely one of the better languages for observability applications. So we wanted to stick with Go, and also Cilium and Go in general has a really active and helpful community that you can leverage if you run into any sort of problems with it. And that is what we definitely did. And we got a lot of help from that. Apart from that, Cilium is a really active project, and it has active maintainers that are always ready to help or take a look at any of the issues that you are having. So basically, your development becomes much faster while using it, and that is what we experienced. But also, there are other options in Rust, C++, and Python. And like, one of the reasons that we did not go for them is first because Rust is definitely more memory safe compared to the other languages, but it has a steep learning curve, and there is not a lot of support for it yet. We were not sure if that would be the ideal way forward if we couldn't get a lot of support, because eBPF itself is a really recent technology. So that too has really limited support and all. So we wanted to go for something with a bit more support. And C plus was getting like really low level for us, and that is what we did not want to do. So we ended up sticking with Cilium. But if you have other requirements, or you do not agree with these reasons, there are these bunch of options that you can go for. So for Rust, you have Aya, and since it is in Rust, it obviously offers better memory safety compared to the other alternatives that we have in Go and C++. But obviously, as I mentioned, it has a more steeper learning curve, and The support is also not as much as Cilium. And for Python, you have BCC. BCC provides you all the libraries that you need for writing your user space code for getting the data, and you also have libbpf that you can in C++. And also BCC and libbpf are actually two of the popular most popular languages used for, not languages, they are frameworks used for writing kernel space code in eBPF. But one major difference between them is that libbpf runs on the idea of compile once, use everywhere. So basically, if you have written your source files, you just need to compile it once, and then you can run that eBPF program anywhere as long as you have the object files with you. But that is not the case with BCC, because you will need to compile it every time that you need to run your eBPF application. The problem becomes that you will need to include your source file in the main repository of your project, which could be a deal breaker for a lot of people. And that is also one of the reasons that we went for libbpf. So we could just compile it once on our end, and we could just use the object files in our main repo, and that would get the job done for us. So it basically depends on your needs and what you prefer. So I just wanted to talk about the user space and the kernel space a bit more. So the user space is basically where your application runs and where all the user side handling happens. So basically everything that you can run and interact with is running in the user space, and it obviously has very limited access to system resources as it is on a very high level as compared to the kernel space. But it is where your users interact with your application, so that's why it is important. And the kernel space is really more low level compared to the user space, and it has direct access to obviously all your hardware, and it typically has really high performance, and it performs all the low level operations for your application. So here we are using eBPF as a bridge so that we can get the data from the kernel space and then use it in the user space, so that we can take advantage of both the kernel space and the user space in our case, and we are able to show the user the most low level data that is possible to be shown. So here is the Cilium, an example of Cilium code that we had used. So basically, after you have written your kernel space code, you just need to compile it, and that would generate objects for you in Cilium. And then you basically need to attach the probes to all the calls that you had. Let me first explain this using a diagram. This is by Pixie, and this explains it really well. So suppose you have an application that is making encrypted calls to a website, right? So in that case, it will first call the OpenSSL library to encrypt its data, and then it will call the send and receive system calls to send and receive that data. So in this case, if you wanted to access the data before it gets encrypted, and if you attached a probe to the send system call, that would not work, because in the data is actually getting encrypted in the TLS library and not the send and receive system calls. Basically, after the application calls the TLS library, it encrypts the data using the SSL read and the SSL write functions that it has, and then after the data is encrypted, it is sent to the send and receive system calls. So if you try to access the data here, all you are going to get is gibberish. So for that, you would need to attach probes to the SSL read and the SSL write functions, because that is where the encryption is happening. So you can access the data before that encryption happens, and you can do all sorts of things with that. So here, that is what we are doing. So we open a buffer to check for all the events on those functions, that is the SSL read and the SSL write functions, and then we attach probes to those functions, like here. And here we are using a uprobe because this TLS library is in the user space and not in the kernel space. So in this case, we are attaching a uprobe. And if we were to attach probes on send, receive, or any of the system calls, we would be using k probes. So in this case, we attach a probe each at the ending and the starting of the function. So here we have a probe at the starting of the SSL write function and one at the ending of the SSL write function. And similarly, we attach probes to the SSL read entry and the exit, and we keep polling for any data that we get, and then we can do all sorts of things with that data. So to demonstrate this, I also have a demo. This is Pixie's demo that I'll be using for showing this. So what we have here is essentially what we talked about. We have a client and a server application that are basically establishing a TLS connection with each other, and then they are sending encrypted data to each other, and we are going to try to get that data using our eBPF program. So let me just show you how the application works first. We start the server here and we start the client here. I've logged PID first of all to use it in our tracer, and this is basically what is happening. It is the server is sending it some secrets, and the client is sending the server some secrets, and they have established an SSL connection with each other. So let's look at the eBPF code that we have for this. So if we go to the tracer, here we have linked it to the OpenSSL library that we have in our machine. That is, so here we have attached it to our library, that is the libSSL library for Linux, and we have attached the probes on the SSL write and the SSL read functions, and we have essentially attached two probes, one at the entry of that of that function and one at the exit of that function. And here at the end, we are just going to be polling these functions for any kind of data that we get. So as you can see in this infinite while loop, we just keep polling for the data as long as the eBPF probes are attached to it. And in terms of functions, we have the functions right here. If you see, so here we have the actual functions that are used in the processing. So first, let's take a look at the SSL read and the SSL write function. So here it is getting the data using this specific register COM2, and we have basically created a hash map that would map the data to its specific TGID, and that is how we are going to be storing it and processing it. And at the end here, we just submit this event so that it could be logged by our tracer. So here, as you can see, we have functions for both SSL read and SSL write, and for the entry as well as the exit. And we obviously get the data here at the entry of each function. So let me just run this and let's see how this works. Let me just start this. Let me start client. So this is our PID, and we run the tracer on this PID. So as you can see, it has attached the probes to SSL read and SSL write, and now we have access to all the data that is being sent over this. TLS connection. So we have the client secret as well as the server secret, and you can verify by looking at these secrets that are being logged in, and we have all of that here. So this is how basically you can use eBPF in your observability application. This is one of its application. You can use it to attach it to a lot more K-probes and go ahead and try and play with it and see what you get. And this has been it for my talk. If you have any questions, you can hit me up on LinkedIn, and I look forward to hearing from you. Thank you.